Hello everyone and welcome back to another video. Today we're going to continue our discussion on modular arithmetic by introducing complete residue systems, and then one of our proofs is also going to involve mathematical functions, so I'm going to introduce that concept as well in this video. So without further ado, let's jump right into it. So from our discussion of modular arithmetic so far, you may have kind of caught on to the fact that it seems like congruence mod n seems to reduce the full set of integers into this smaller set of numbers all below n. It seems like you can reduce the whole integer line into the smaller set of numbers with congruence. However, we haven't proved this or formally defined this in any way so far in our discussions. We've just kind of set the groundwork for modular arithmetic. So let's use this video to do just that, and we're going to introduce the concept of complete residue systems. But first, there's a very foundational theorem to all of this in defining complete residue systems that we need to prove explicitly first. This is theorem 3.14. Has nothing to do with pi, though. So theorem 3.14. And this one is basically saying, given any integer and any natural number n, there exists a unique integer t and I don't know if you guys can hear the cats. I think they know when I'm recording because they always just come up and start crying at the door right when I start recording. Unique integer t in the set zero, 1, and then all the way through n minus 1, such that A is congruent to T mod n. Okay, so that's the basic statement. It's basically saying you can pick any integer and then the natural number n for the mod that you're gonna apply, and then it's basically saying you can find some unique integer in that set 0 through n minus 1, such that, and it's a unique integer, that's a crucial part of this proof too, such that A is congruent to that integer. So it's basically reducing it to this number that it's congruent to under n, a positive number under n. I guess 0 is not positive, but positive numbers or 0 all under n. So for our proof, we're going to start by just defining A and n. Messed up that a little bit. Okay. And then, now the one thing that you might notice is that having this set 0 through n minus 1, we've actually seen this set before in something we discussed way earlier in our discussions of the number theory way at the beginning. And this is the division algorithm. And we're going to use that here in this proof. Then, by the division algorithm, A equals NQ plus R for some unique, this is crucial, Q and R in the set of all integers, where R is in this set. And if you're thinking ahead here, you might actually see, you can probably guess now that R is actually going to be this T that we're trying to find, because it is in this set, and what we're going to talk about next. Oh my gosh. I'm like getting right up to the side of the page. I think that's fine. You can see that's n minus 1. I'm being way too pedantic on my own handwriting here. So then, therefore, A minus R equals NQ. Just rearranging the equation a little bit. So, by the definition of congruence modulo n, so A is congruent to R mod n. And then note here also, R is the only integer in this set where this equation is satisfied. Because if we have a different R from that set, then Q would have to be different. It would mean that A minus R equals NQ for some different value of Q. But then this would not be a unique solution to the division algorithm. So this R that we found exists in this set of numbers 0 through n minus 1, and it's unique. It uniquely satisfies this equation here that shows congruence. So since R in this set is unique solution to division algorithm, I forgot an H, and now it just looks bad. I'll rewrite that one. Algorithm R is a unique integer in the set. I'll say unique integer T. We'll just redefine it as T in the set, just to kind of match the language of the proof. N minus 1 is a unique integer in that set such that A is congruent to T mod N. Okay, so that is our proof. It basically shows that for any number that you choose, you can find a number that is congruent to mod n that is less than n and is positive or 0. So based on this theorem, there's this sort of implicit implication that there is this one set of numbers in which every natural number is congruent. You can kind of reduce the whole integer line into this one set of natural numbers. And this set is actually called the canonical complete residue system modulo n. So let's define that quickly. The implication is you can reduce any number in the natural number line into somewhere in this system. It's congruent to something within this set of n numbers here. And this first one is called the canonical complete residue system modulo n. So very, very wordy name, but that's what it's called. And it's going to get a little shorter because we're not going to stick to only focusing on the canonical one. We're going to see that there's actually other ones where this holds. Let n be a natural number. Oh, it's like internet security thing. I think those things were like very common or very important back in like the early 2000s, but I don't know how relevant they are anymore. So let n be a natural number, the set 0, 1, ... n minus 1 is called the thing we just said, canonical. And see, now this is rhyming with some of my other content too. We're talking about the canon again. No, the canonical complete residue system modulo n. Now, one thing to note about this, so we have this canonical complete residue system modulo n, where every number in the natural number line is congruent to one of these numbers guaranteed for modulo n. But this isn't the only example of a collection of integers that represent all integers modulo n. Another example, so we have this one. This is canonical. This is the canonical complete residue system. CRS. I'm going to use this acronym a lot throughout the rest of this. But another example would just be this. And this has the same property, where what you can do is represent all integers modulo n just with this set, every single number, because 0 is congruent to n, and then all the other numbers are all the other congruences that we already have covered. So in this sense, you can actually, any number that you would have in the canonical complete residue system would have wrote as equivalent to 0, you could just write it as congruent to n. So that would also be another example. So we need a more general definition besides just the canonical complete residue system. So let's actually give this here. So the definition is, let k and n be natural numbers. A set A1, A2, ... I believe they use k, but we're actually going to prove later on that k has to be equal to n. That's going to be the next proof of integers is called a complete residue system Okay, and that's going to be the last time I write out fully complete residue system. I'm going to start writing CRS from now on. Complete residue system modulo n if every integer is congruent modulo n to exactly one element in the set. So obviously some examples of CRS might include, so let's think like complete residue systems mod 4, for example. So let's think of some examples. Obviously the first one would be the canonical complete residue system. So you would do 1, 2, 3. But another one could be, like we discussed before, 1, 2, 3, 4. Or if we wanted to come up with another one, we could even start having gaps between the numbers. 1, 3, 4, 10. And this works because 10 is congruent to 2 mod 4. So anything that was congruent to 2 mod 4 originally, we can just say is congruent to 10, just by the transitive property theorem 1.11, which we're actually going to cite more in this particular video. But another one, if we wanted to go even higher, we could go 101, 102, 103, and 104. So those are some examples of complete residue systems. And now one pattern you might have noticed in all these complete residue systems, and this makes sense intuitively if you think about it a little bit, but we're going to prove it relatively soon. All these sets are of size 4. The cardinality of each of these sets is 4. Is that always true? Yes. But we have to go ahead and prove that later on. But before we do that, one technique that we're going to use in our proof is proving that 2 sets are the same size using a bijective function, showing that if the bijective function exists between two sets, then the 2 sets have to be the same size. So let's go ahead and prove that quickly, or let's start by introducing functions very quickly. This is going to be a brief introduction, so if you are lost or behind or anything on any of this, that's fine. I just want to introduce the concepts first so that we can actually functionally use this proof. So, for example, you might be familiar from like functions from algebra. A basic example be like f of x equals x squared. And then it has like the parabola shape, blah, blah, blah. It looks like that. But it basically, what a function does is give us this rule where we can input anything within the function's domain. So in this case, the function's domain would be any real number on the real number line. And then we will get some unique output. Like if we put in 0, it's not like sometimes we're going to get 0 and then other times we're randomly going to get -10. We put in one number, we're going to get out the same thing from that function every time, which is crucial in kind of understanding the definition of functions. But functions don't just have to exist between sets of real numbers. Like in algebra, you'd always see your input is a real number, your output is also a real number. That doesn't always have to be the case. A function is a much more general idea than that. It relates to moving something by a defined rule from one set to another set in a way where if you put one number in, it corresponds to a unique output. So let's write out this definition more formally. This is actually from the book of proof, which is what I used in my introduction to proof videos. So it's kind of a callback to that series. I don't think I actually introduced functions in that series though. But let's briefly introduce them here because we need some property of them to do this proof later on. It's not necessary, but I think it makes the proof a lot cleaner, and I feel like this is a good opportunity to introduce them. So our definition is suppose A and B are sets. A function f from A, which we're going to call its domain, to B, which we'll call its codomain, and then the way we're going to denote this is f A to B, and then you also do like x to f of x. That is where you can actually like explicitly define it. So yeah, that's the denotion. It's a relation F being a subset of A x B. And this, I think we introduced this in our set theory idea, but it's just taking every combination of A and B and putting it together. So F would be a subset of that because you get this ordered pair that comes out that would have A and B. But that's a less crucial point about how exactly, and if you don't understand what exactly I mean when I say it's a relation, where it's like a subset of this, that's not as important as understanding like the general concept. From A to B, satisfying the property, and this is important for the uniqueness point, that for each A and A, the relation F contains exactly one ordered pair of form AB. The statement A, B are contained by F is abbreviated F of A equals B. So you plug A into this function F and it gives you B as an output. So just to think of some other examples of this, just besides what we have already seen, say, in like algebra classes in high school. Another way we could define it, we could do something from the integers to the natural numbers, just bringing this into more of a number theory context here. And then it could be to like that. So it's just basically saying this function moves us from, you can plug in any integer, it's going to output a natural number, and that natural number output is going to be the absolute value of the integer you plugged in plus 2. So for example, f of 1 is 3, f of negative 5 equals 7. And now another thing we can talk about, we can generalize this a little bit to any set of things. So for example, set of students to set of desks. And the exact rule can be however you want to define it, but this is basically like a seat assignment process. So this is the way you could think about this. Like say you have 3 students and then 4 desks. The function could be you input each one of these students and it outputs the desk number they're assigned. So he might go here, this person might go here, and this person might go here. And there might be one left open, for example. Another example, you could have the same 3 students, and in this case, they might have to share a desk. So the output itself doesn't have to be unique necessarily. So 2 people might have to share a desk. So two inputs might have the same output. But the important thing is that this person can't be sitting at 2 desks at once. The desk could have 2 people sitting at it. For say it's like a big desk or something. But you can't have the same person sitting at 2 different desks. You can't have the same input going to 2 different outputs, but one output could be from 2 different inputs. Now, if we want to get more specific about functions where every output only has one possible input. That's what we're going to get into now. So now we're going to introduce other concepts that specify properties of functions a little bit more. And this is where we actually get into the useful stuff for like set sizes and doing proofs about the sizes of sets. So let's start with a function. Very general, f from a to b. And first, it's injective, or you'll hear 1-to-1. And this, basically, the formal statement of it is for all a and a, for all a and a prime and a prime and a, f of a equaling f of a prime implies that a equals a prime. So this would basically mean, this is basically like saying that every assigned desk, so every desk that is assigned, there could be unassigned desks, so every assigned desk only gets assigned one student. There's not two people sitting at a desk. One output doesn't have two possible inputs. That would mean it's an injective function. There's also one thing to note, is this implies that a is less than or equal to b. And that's by the pigeonhole principle, but let's explain this a little bit more intuitively. So if every desk has one student, there must be fewer students than desks. Because the second you have more students than desks, then somebody has to share a desk. So then the function of seat assignment in this context would not be injective, because people have to share desks. On the other hand, if you have more desks than students, it is possible that each student only gets assigned one desk. Each input only corresponds to one output. So you would need a set that is larger to be the output, if you want injectivity to be true. Basically, injectivity implies that your codomain is larger than your domain. On the other hand, you have surjectivity. And this is also called onto. So a function can be onto. And the way to state this is that for all b in codomain, there exists an a in the domain, so in the input space, where f of a equals b. So this is basically saying every desk gets assigned, but it's possible that two students could share a desk. Every single element of the codomain has some corresponding element of the domain where the function produces it. So the entire codomain is covered basically by the function. Now it's possible well, in this case it would be possible that you could have two things corresponding to the same element in the codomain, but having different inputs. So two different inputs could create the same output. So in this case, it is possible that in that sense there are more students than chairs. So what that implies is that the cardinality of the domain is greater than or equal to the cardinality of the codomain. To understand why that is, if you look at this example where there are 4 desks and 3 students, there are too many desks. There's too many outputs that that they could go to for them to cover all of the outputs. But in this case, when there's more students than desks, there are enough outputs. They can double up. But they can cover every single desk. They can cover every single output. And then finally, Since these aren't mutually exclusive, they could both be true. Bijective is when a function is injective and surjective. And what does this mean? Well, it means that A is greater than or equal, the cardinality of A is greater than or equal to B, and the cardinality of A is less than or equal to B. So what is the only option? Well, let's just write this out. If A is less than or equal to B, or if the cardinality of A is less than or equal to the cardinality of B and is greater than or equal to the cardinality of B, that literally just means that the cardinality of A is equal to the cardinality of B. And this can be useful in proofs when we're trying to think about how large a certain set is, which is exactly what we're going to do next. How much space do I have over here? Oh, I'm good. Okay, we're good. So let's switch back to complete residue systems. So now that we have this concept of function kind of established, we can see how it's useful for discussing the sizes of sets. Now we want to prove something about the size of these sets that we just talked about, complete residue systems. So theorem 3.16, and this theorem states let n be a natural number every CRS mod n contains n elements. And then for our proof, so we're just going to start by defining n. Let n be an integer, let n be a natural, and let S be a complete residue system mod n. Then consider the set, which is actually the canonical CRS that we're going to define here. Consider the set S prime equals this, n minus 1. So S prime equals n. Also, I guess to kind of think about why it's important to prove this, we should think about the alternative a little bit. The alternative would basically be there's some CRS that you can come up with out there that has n minus 1 elements, and then every single integer is congruent to one of these numbers mod n. Or it would take more, like there's some CRS that would take more than n elements. So yeah, that's essentially why we need to prove this, just to show that it is every single one contains n elements. We know like the canonical one does, but we need to show that every single one does. So what we're going to do is define a function, because we need to prove that the cardinality of S equals n. We already know that the cardinality of S prime equals n, just because we can count its elements. So we need to prove that about S, and that's kind of the goal of this proof. And we're going to do it by showing that the bijective function exists between S and S prime. So we're going to let f be the function S to S prime, where for an element A in S, f of A, this is just defining the set, is the unique I need to finish my words before I start writing the next one. is the unique integer in S prime such that A is congruent to f of A mod n, which we know exists and is unique by theorem 3.14. Citing theorem 3.14 here is important just to show that this function is well defined. Like, this is actually a function that we can do. It'd be like if it wasn't well defined, it'd be the equivalent of like trying to create a function where the domain is the negative numbers and it tells you to take the square root or something. And I guess that's fine in complex analysis, but in other fields, assuming you're not in complex analysis, doing something like that, or having like an ln or like a natural log instead of a square root, that makes it a lot worse as well. But okay, so that's step one. And now we're going to start by proving injectivity. So we're going to start by just defining these numbers in S, x1 and x2 be in S, and R1 is going to be in S prime, such that, so we're setting up this first step here, such that f of x1 equals R1 and f of x2 equals R2. And if we can prove that x1 equals x2, then we've shown that the function is injective. So then x1 is congruent to R1 mod n, and x2 x2 is congruent to R1 mod n. But remember, in the definition of a complete residue system, it's mentioned that every integer is congruent with congruent modulo n to exactly one element of the set. This is the same number, but it's congruent to two different numbers in this complete residue system. And we said that S is a CRS. We said that S is a complete residue system. So really the only option is that these are the same number, because then otherwise you would have one number that is corresponding to two different, that is congruent to two different integers in a complete residue system, which means it's not a complete residue system. So basically, by the definition of CRS, x1 equals x2, so f is injective. Okay, so that's the first part. That's the first part of it. And then for the next part, we're going to prove surjectivity. So we're going to start by letting R2 be an element of S prime, which is an element of the codomain. We need to show that basically that there's a number in the CRS above that we defined that corresponds to, that is congruent to R2. There needs to be some number in the CRS that the function would map to R2. Well, what we know by the definition of a CRS again, the specific wording is, let me find it again. it's called the complete residue system modulo n if every integer is congruent modulo n to exactly one element of the set. So every integer has to be congruent to an element of the set, including R2. So once again, by the definition of CRS, there exists an A in S such that A is congruent to R2 mod N. And what that means is that f of A equals R2. So f is surjective. And therefore, let me scroll down a little bit. Our function, since it's injective and surjective, our function is bijective. Consequently, let's use a new word. Consequently, or I guess before that, let me just write it out explicitly. So there exists a bijection, it's F, between S and S prime. And remember, earlier we said that S prime has a size of n. So there exists a bijection between S and S prime. Consequently, the cardinality of S equals the cardinality of S prime, which equals n. So S, the size of that set, the number of elements in that set, must be n. It can't be any larger, it can't be any smaller. And that is what that proof goes through and demonstrates. So, with that in mind, we know what the size of a CRS is, but the question is, like, how can we generate one? What are the properties of these actual numbers? Can we know anything about them? What else do we know about these complete residue systems that we just have been talking so much about in this video? So the next theorem is going to give us insight into specifically which n numbers must come together to form a CRS mod n. So this is theorem . And this theorem goes, theorem 3.17, and it goes, let n be a natural number. Any set A1, A2, AN of integers of n integers for which no two are congruent is a CRS mod n. And we could kind of see that in our example of CRS's mod 4 that we looked at before. When putting these together, I was just trying to think of, like, what are four numbers that aren't congruent, where none of them are congruent mod 4? Put them together, then you have a CRS. So in this theorem, we're going to actually go through and explicitly prove it. So what we're going to do is let n be n, and a2 dot 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 an all be integers such that ai is not congruent to aj mod n when I is not equal to j. So basically all this is doing is defining all these integers as integers where no two are congruent mod n. So now we have this set basically that we're trying to evaluate. So what we're going to do is suppose for contradiction that a1 a2 dot 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 an is not a CRS mod n. Okay. Then there either exists some integers. I guess so basically now we have this set. What would it mean for it to not be a CRS? Well, basically it would mean that there's some integer that isn't congruent to any of these integers in this non-CRS set of integers, or there's some integer that is congruent with two or more. That would show that it's not a CRS. Otherwise, then it fits the definition. There either exists some integer, and I guess both of these could hold too, but such that said integer is congruent to no elements in the set or to at least two elements in the set. Okay, so I want to show how each of these possible directions that you can go lead to a contradiction. So the first one, suppose, let me make this like an actual one. Okay, suppose x is an integer, is not congruent mod n to any elements in the set. And I see my face is covering up what I'm showing. Any elements in the set. Okay. So since AI is not congruent to AJ mod n for I does not equal j, then and this set is of size n, and all integers are congruent to exactly one integer in the canonical complete residue system, by theorem 3.14. Each integer in that in that canonical complete residue system is congruent to an integer in this one. Because basically you're just going through and assigning each of these n integers to exactly one of these integers in this system. And we know that none of them are congruent to each other, so once you take up one with another one of the integers in a1 through an, then you can't take that one up anymore. So you just go through and keep placing them in each of these buckets, and then at that point you have shown that every single one, you'll get through all of them from 0 through n minus 1. You'll show that all of them, all of the ones in 0 to n minus 1 is congruent to exactly one integer in a through n, in a1, a2, all the way through an. Oh, sorry. In this bigger set, I have to write out the whole set. Okay. So now turn the page. So by theorem 3.14, x is congruent to a mod n where a is contained by this set and then also ai is congruent to a mod n where I is in this set. Thus, x is congruent to ai mod n by theorem 1.11. Which is a contradiction, which contradicts the assumption that x is not congruent to any elements in the set. Okay, so that's the first thing. So we're showing that there's not a number that is not congruent to any elements in the set. So now we need to show that there is not a number that is congruent to multiple elements in the set. So suppose, now we're getting down to the end, which is good because we're almost done. Dang, still comes in almost at an hour. This felt like a quicker script to write too. Suppose x is an integer and is congruent to at least two elements in the set. And then without loss of generality, we're just going to assume that these are the first two indexed elements. We can change the indices all we want. But without loss of generality, suppose x is congruent to a1 and x is congruent to a2 mod n. Thus, a1 is congruent to a2 mod n just by the transitivity, by theorem 1.11 again, which ultimately contradicts the assumption that AI is not congruent to AJ mod n for I not equal to j. Okay. So that is all for this video. So basically what we showed here is that if we get any set of n integers where no two are congruent, it has to be a CRS, because no matter what we do, whether we suppose that there's some number that isn't congruent to any elements in the set, that leads to a contradiction, or we suppose that there's some integer that is congruent to at least two elements in the set, that also leads to a contradiction. So if we have this set, it has to be a CRS. Every element has to be congruent to exactly one element in that set. Can't be 0, can't be 2 or more. Has to be exactly 1. Thus, it must be a CRS. So that's ultimately what we showed about complete residue systems. And with that, we got through a pretty foundational concept in modular arithmetic, and then we have some very preliminary facts established about it. And yeah, with that, I'm just going to open it up to the comment section. I hope you guys all enjoyed, and then next week we're just going to continue this discussion of modular arithmetic. Chapter 3 is a little bit of a slower, a bit drier chapter than some of the other ones. It's less related to a lot of the math that you may, more of the popular level math, like the prime stuff obviously was going to be very popular and all that and get a lot more views, but obviously this we're just kind of working through and setting up a lot of foundations for what's to come, because all of this is pretty crucial for some deeper number theory concepts. Like modular arithmetic is very handy, and a lot of these theorems tend to be very key later on in the course. But yeah, so next week we're going to continue discussing modular arithmetic, continue on chapter 3, and we'll just keep going through it. And I hope you guys are enjoying. I think we're going to get into a little bit more practical stuff next week, like actually looking at solving equations with modular arithmetic. Just looking at a brief glance ahead. I haven't started prepping that material yet. But yeah, be on the lookout for maybe a live stream, maybe some more theology content next week. Yeah, I need to get back on that horse. Yeah, I mean, I have been posting a lot of theology content too, nonetheless. But I wanted to get some of this math stuff, get through some of this math stuff to get on to lay some of the foundation so we can get on to more interesting, popular level sort of stuff. But yeah, so that is all that I have to say for today. If you guys enjoyed the video, go down, hit the like button. There's also a subscribe button if you really like the content and want to be notified of more of what I do. There's also a Discord down below if you want to ask any questions, start up the community, join the community. Totally up to you. There's also Patreon down below if you really enjoy my stuff and want to give me some motivation to keep putting this stuff out there along with my 9 to 5. Which yeah, well we're grinding out here. Also studying for a bunch of like professional exams and certifications. So life is a little bit busy, but yeah, if you want to incentivize me to keep posting this content, there is the Patreon link down below. But no pressure either way. And yeah, with all that, thank you all for watching, and I hope to see you all in the next video. Peace.